Good morning, everyone. Today, we are going to learn about one of the most important topic in artificial intelligence called planning and acting. Imagine you are a robot tasked with moving packages between cities, or you are playing a chess and need to think several moves ahead. How do you decide what to do? That's where planning comes in. Planning is how AI agent think ahead, decide on a sequence of actions, and then execute them to achieve objective or goals. This is what separates intelligent agents from simple systems that just react to what's happening around them. What's the planning in AI? Let me define planning clearly. Planning is a process of generating a sequence of actions which leads from where you are now, called initial state, to where you want to be, called goal state. It automates reasoning about actions and lets agent exhibit intelligent behavior over extended time periods. Think about in this way. A robot needs to move from point A to point B while avoiding obstacles. A logistic company needs to schedule delivers optimally. A game playing AI needs to think multiple steps ahead. All of these require planning. The key difference from traditional problem solving is that planning uses explicit representations of both states and actions. We don't treat them as a black boxes in a conventional system. We understand their structure and effect. The core component of a planning system, like initial state, goal state, action, or operators, plan. Initial state, this is where we start the current configuration of the world before any action. For example, a robot in a warehouse position A with certain items on shelves. Goal state. This is where we want to end up, the desired configuration. Maybe all packages are delivered and the robot is back at base. Actions are operators. These are all operations available to us. Each action has a precondition, what must be true to execute it, and effects, what changes after executing. For instance, pickup box might require the robot to be next to the box and it changes the state, so the robot now hold the box. Finally, plan. This is the ordered sequence of action that transforms the initial state into the goal state. The plan is what we generate and then execute. In a real world example, a logistic system moving packages between cities, it must plan the route and the schedule, the sequence of deliveries, and also ensure all constraints that meet. Strips, a foundation for planning. So STRIPS, STRIPS, it stand for Stanford Research Institute Problem Solver. So it's one of the most influential planning representation in AI history, and it's elegant in its simplicity. In steps, each action is defined by three components: precondition, add list, and delete list. In precondition, fact facts that must be true in a current state before the action can execute. Think of this as requirement. For example, to drive a car, the preconditions might be car is fueled, driver has a license, etc. called preconditions. Second, add list. New fact that become true after the action executes. For instance, after drive to work, the add list includes agent is at work. Delete list. Fact that become false after the action executes. After drive to work, we delete agent is at home, called delete list. Let me give you a concrete example with the blocks. Action, stack of A comma B. Stack block A on top of block B. Preconditions, block A is clear, nothing on the top. Block B is clear, agent is holding a block A. Add list on A comma B. Now A is on B. Delete list, clear of B and holding of A. B is no longer clear. Agent is no longer hold A. So step forces you to think carefully about what changes and what doesn't when an action happens. Partial order planning. It's a more flexible. Here's an interesting question to the students. If you need to make a coffee, do you have to grind beans before boiling water? The answer is no. These two actions are independent. This is where partial order planning POP comes in. In traditional planning, actions are strictly ordered, like action 1 and then action 2 and then action 3. But in POP, actions are ordered only when necessary, when one action depends on another. What are all the key advantages in this partial order planning? It enables concurrent or parallel actions, grind beans and boil water at the same time. It avoids unnecessary sequencing that might wasting the time. Third, produces more flexible general purpose plans. Finally, can identify opportunities for parallel execution in robotics or distributed systems. A, a plan in POP consisting of first a set of action, second ordering constraints, third casual links. So ordering constraints which action must come before others. Casual links connections showing why one action is needed for another. So instead of rigid sequence like action 1 and after that action 2 and after that action 3, you might have action 1 and action 2 happening in parallel, both feeding into action 3. This is more like how humans actually plan. We think about what needs to happen, not necessarily the exact order. Planning in real world, theory is nice, but real world planning is messy. Here, the challenges we faced are one, it's a dynamic environment. Third, incomplete information. Third, limited sensing. First, dynamic environment. The world changes. A robot plan a route, but a new obstacle appears due to traffic condition changes and weather happens. Second, incomplete information. We don't know everything. The robot can't see around comes. Third, limited sensing. Cameras, sensors, and other instruments have their own limitations. To handle this, AI systems use different approaches. First, reactive agent. These respond directly to what they perceive without explicit planning. It's like a reflex. You see something hot, you pull your hand back immediately, fast but limited in complexity. Second, deliberative agent. These carefully plan everything before executing, like a chess player thinking through possibility, most intelligent but can be very slower. Third, hybrid agent, the best of both worlds. They plan strategically for long term goals but react tactically to immediate situations. This is what self-driving cars do. They have a long-term routes plan but react immediately to a pedestrian stepping into a road. Real-world applications are self-driving cars, service robots, and game-playing artificial intelligence systems. Belief network, reasoning under uncertainty. In the real world, we rarely have complete certainty. We have probabilities and uncertainty. This is where belief network, also called Bayesian network, come in. A belief network is a graphical model that shows node edges and CPT. So node are random variables like weather, traffic condition, and arrival time. Edges are casual dependencies between those variables. CPT, conditional probability tables. It's a numbers that quantify relationship. For instance, for example, weather can be sunny, rainy, or cloudy. Weather affect traffic conditions. Traffic conditions affect arrival time. So, if I know the weather is rainy, I can update my belief about traffic. It's probably heavier, which then updates my belief about when I will arrive. A key mathematical property, each node is conditionally independent of non-descendant given its parents. This means the network is incredibly efficient. You don't need to store all the possible combinations, just the local relationships. Belief networks are used everywhere, like medical diagnosis. Based on the symptoms, we are going to identify the diseases, weather prediction, and traffic forecasting, and spam detection. Now we will move to the topic of inferences and decision making. Once you have a belief network, how do you use it? First, inference. Inference means computing. What do you want to know based on what you observe? For example, given that it's raining and traffic is heavy, what's the probability I will arrive late? There are exact methods, mathematically precise but computationally expensive, and approximate method, which is faster but less precise. But inference alone is not enough. You also need to make decisions. This is where decision theory comes in, combining probability with the utility. The formula is EU of action equal to summation of probability of outcome of action into outcome. In For your better understandability, the expected utility of an action is the probability of each possible outcome times how much that outcome is worth to you, summed up. For example, should I take an umbrella? If I bring it and it rains, good outcome, utility equal to 10. If I bring it and doesn't rain, slight inconvenience, utility is equal to 8. If I don't bring it and it rains, bad outcome. I get wet. Utility equal to 2. If I don't bring it and it doesn't rain, good outcome. Utility equal to 10. If the probability of rain is 30 percentage, then E of bringing umbrella equal to 0.3 into 10 plus 0.7 into 8. So total equal to 8.6. Probability of no umbrella, the calculation is 0.3 into 2 plus 0.7 into 10 equal to 8.0. So bring the umbrella, which is higher value. We have 8.6. This principle, maximum expected utility, MIEU, is the foundation of relational decision making in AI. Next, we have a theory called Markov decision process, MDPs. Many real-time decisions play out over time. You make a decision, something happens, then you are in a new situations and must decide again. This is where Markov decision process comes in. An MDP have a five key elements: state, all possible configuration of the world; action, what you what you can do in each state; transition, probability of moving between state; reward or immediate feedback for being in a state or taking in an action; policy, your strategy, a mapping from states to action. The goal is to find the optimal policy that maximizes the total reward over time. Some of the real world applications are a robot navigating a building, state or location, actions or movements, rewards are reaching the goal. Second example, inventory management. States are stock levels, actions are orders, rewards are profit minus storage cost. The foundation of modern machine learning called reinforcement learning. Solution methods like value iteration or policy iteration help find the optimal policy. One key concept is discount factor of Y, which balances both immediate reward and long-term reward. Immediate reward is like what happens now. Long-term reward is like what happens later. A robot mind chooses a path that seems bad now but leads to a great outcomes later. That's because it's thinking ahead with the discounting. So, as a conclusion and a takeaway of this class is planning bridges, reasoning, and actions. We explicitly represent state actions and their effect. This lets machines reason about consequences before acting. Steps and partial order planning are formal ways to do this. Second, real world demand integration. Successful artificial intelligence systems are not purely planners or purely reactive. They combine strategic planning with tactical reaction, adapt through replanning, and learn from experiences. Uncertainty requires probabilistic reasoning. We use belief networks and decision theory to reason when we don't have complete information. This is crucial for realistic systems. Sequential decision need structural approaches. MDPs and related framework provide a mathematical foundation for optimal long-term decision making, and they are fundamental to modern reinforcement learning. So, intelligent behavior require planning, from robot moving through warehouses to autonomous vehicles navigating cities to AI players. Planning is how machine achieve complex goal intelligently. Thank you all.